So this is problem A, good subsequence. A subsequence B is called good if bi mod 2 not equal to bi minus 1 mod 2. So, am I audible? Hello, hello, hello. Okay. So let's start with problem A. Good subsequence. A subsequence B is called good if bi mod 2 not equal to bi minus 1 mod 2 for all I from 2 to length of bi. For example, 1, 2, 3 and 1 and 4 are good subsequence, but 1, 3 is not because 1 and 3 are both odd. You are given an array A of length n. Find the longest length of largest subsequence of A that is good. Okay, so constraints are T is still 100, N is still 100, and AI is still 100. So basically expected time complexity would be around O of N square or O of N into AI, since that would be 10 to the power 6 operations. Okay, so let's see the test cases. Problem A. So basically the problem is to find the largest subsequence such that no two consecutive elements are both even or both odd. Basically, bi mod 2 not equal to bi minus 1 mod 2. Bi mod 2 not equal to bi minus 1 mod 2. Mod 2 means the remainder when I divide bi with 2. So let's see the test cases. 11263, 11263. So if I take this one, then the next number I'll have to take an even number. So I can take this, and if I take this number, the next I'll have to take an odd number. So basically I'll have to choose a sequence like this: odd, even, odd, even, odd, even. Or I can choose even, odd, even, odd, even, like this. Or if I had not chosen this one, then if I had chosen this one, then again the answer would have been the same. And if I had chosen this 2, then I'll have to pick this 2, and then I can only pick this 3. So basically the longest subsequence would be 1, 2, 3, which would be of size 3. So answer for this test case will be 3. 100, 198, 97. So 100, 198, 97. So if I pick this 100, then I'll have to pick this one, and then I can pick this 98, and then I can pick this 97. So basically I can pick all the elements. So answer for this test case would be 4. 1, 5. So basically if I pick this one, then I won't be able to pick this 5, and if I pick this 5, then there aren't any more numbers. So answer for this test case would be 1. So basically we are getting sub problems here. Let's analyze for this test case. We had 1, 1, 2, 6, 3. So when we had picked this one, now we had a sub problem that we need to find the largest subsequence in this array when the last element we used was an odd number. So if since the last element we used was an odd number, we had to pick this 2 as the next element, and then we had a sub problem that we need to find the longest subsequence in this array with the last element used being an even number. So again, since the last element we used was an even number, then I had to pick this 3, and then we didn't have any more sub problems, so we can say the answer is 3. So what we can do is we can write a DP based on the sub problem that we observed here, and it would be like this. Let me define the state. The state will be DP of I comma last, which means that this holds the answer for from last to n. Sorry, from I to n, where last can be 0 or 1, which tells us whether the last number we chose before this array was an even number or an odd number. So what will be the transitions? We can do DP of I comma last. Basically, we can always not choose the ith index no matter what. So one possible answer would be DP of I plus 1 comma last. And the other possible answer would be DP of I comma last plus 1. Sorry. I plus 1 comma basically last XOR 1 plus 1. Basically last XOR 1 is simply if last was 0, then it will be 1, or if last was 1, then it will be 0, basically flipping the parity. And this transition is only possible when the array A of I percentage 2 is not equal to the last. If the ith element has a parity which is not equal to the last element that we chose, then we can perform this transition. And the max out of these two would be the answer. So let's try to dry run this DP on a test case. Let's take 11263. So 11263. So let's just basically the final answer for this question would be DP of 0, 0, sorry, maximum of DP of 0, 0 and 0, 1. Basically, we can we need to find the answer for both if the first number that we take is an even or the first number that we take is an odd. So depending on what we do, we can take max of both, and that would be the answer. So let's try to find DP of 0, 0. So since last was an even number, then I need to take an odd number. And since this is an odd number, so I'll have these two transitions, DP of 1, 0 and 1 plus DP of 1, 1. And further from DP of 1, 0, again, index 1 also has an odd number. And since the last was an even, so again, I have this transition 1 plus DP of 2, 1, or I could have just skipped and gotten this transition 2, 0. Also, from this, now since 1 is odd and the last number is also odd, so I cannot take the number at index I. So this will give us the transition DP of what 2, 1. And again, since DP of 2, 1, since 2 is an even number, then we'll have this transition DP of 3, 1, 3, 0 plus 1. And since 3 is even, we won't be able to take it. So this will give us the transition DP of 4, 1, which we can take, and we'll get the transition this. And let's imply the base case when I is equal to n, return 0, because there aren't any more elements that we can add to our subsequence. So this is our base case. So this will result to 0. So the value of this will be 1. So the value of this will be 1. So the value of this will be 2. So the value of this will be 2, and 2 plus 1. So this will be 3. So that's how we are getting our answer. We can also explore further here and here, we will just get the same answer. So basically, we can verify, right? Because let's just look at this state. We got the answer as 2 for dp of 2 comma 1. dp of 2 comma 1 basically means 0 1 2 3 4, basically means for this array, if the last element I had taken was odd, what is the maximum subsequence length I can get? So I can pick this element and then I can pick this element, so the maximum would be 2. That's our answer for this. So basically, let me again just write the states. So dp of I comma last gives the longest subsequence starting from I till n with the last element taken being of parity last. And what would be the transitions? The transitions would be maximum of dp of I plus 1 comma last. This simply is the state of not picking the current element, comma dp of I plus 1 comma last or 1. This is the state of picking the ith element, which is only possible when a of I mod 2 is not equal to last, since only then I can pick the ith element. And last or 1 basically flips the parity for this new subproblem. So what will be the time complexity of this? Time complexity of a DP is total number of states into average transitions per state. So basically total number of states is 2n, since each state has two possible last values, 0 and 1. And average transition per state would be a maximum of 2. So overall time complexity would be 2n into 2 is O of 4n, which is simply O of n. I'll show you guys the code for this. So basically dp of I comma last, and this is the base case. If I is equal to n, return 0. And the answer would be max of dp I plus 1 comma last, or if the current element has a parity different from the last element, then 1 plus dp I plus 1 comma last or 1. And this is basically for memorization. And this is input. And then I see out maximum of dp 0 comma 0 and dp 0 comma 1. The time complexity for this question is O of n. So now let's move on to the next question. So for a string S, we define fs as the number of distinct palindromic substrings of S. For example, f of ABAA is equal to 4 because we can find the palindrome substrings AB, AA, and ABA. Call a string S good if fs is less than equal to 5. That is, it has at most 5 distinct palindromic substrings. You are given an integer n. Construct any good string of length n using only lowercase Latin characters. It can be proven that at least one good string exists. You are allowed to print any good string. So constraints are t is 100 and n is still 100. So basically n square would be the maximum time complexity that we can use, or maybe even n cube. But so problem B. So basically we need to construct a string such that the number of palindromic substrings is less than equal to 5. Let's see the test cases, 2 and 4. So for 2, we are given the answer AA, because AA will have two different palindromic substrings, A and AA. For 4, we are given the answer ABAA, because ABAA will have A and then B and then AA and then ABA, these 4 palindromic substrings. So since 2 is less than 5 and 4 is less than 5, so this will be a correct answer for this test case. So one observation is that any string of length 1 is a palindrome. Basically, this A and this B, also they say these are all strings of length 1 and they are a palindrome. So basically, because of this, we cannot use more than 5 characters in our string, because if we use more than 5 characters in a string, let's say we make a string like this, A, B, C, D, E, F, G. Then this will have A, B, C, D, E, F, and G. All of these would be palindromes. So it will have 1, 2, 3, 4, 5, 6, 7 palindromes. So basically, we cannot use more than 5 characters in our string. So let's just stick to using A, B, C, D, E only. Let's stick to using A, B, C, D, E. Now, since we need to minimize the palindromes, right? We need to minimize the number of palindromes. We need to actually make them less than equal to 5. So what we can do is, let's say there is a palindrome. So let's first of all make sure that no two consecutive elements are same. What will this do? Basically, what will this do? Let's say there is a palindrome of even length. Let's say there is a palindrome of 6 length. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. So basically, these two will be same, and these two will be same, and these two will be same. So for an even length palindrome, the middle elements will always be same. So for an even length palindrome, the middle elements will always be the same. So if we make sure this thing, that no two consecutive elements are same, if we make sure that no two consecutive elements are same, what will happen is that there won't be any even length palindrome. So this is a good start. Due to this, no even length palindrome will exist. Since there are no two consecutive elements same, so an even length palindrome can never exist, because the middle elements has to be same. So let's now try to figure out what we can do about odd length palindromes. So let's take a palindrome of length 7. 1, 2, 3. 1, 2, 3. So these two will be same. These two will be same. Sorry. these two will be same, and these two will be same. So basically, what is happening is, let's take a look at these three elements, because these three elements would be in this specific configuration for all odd length palindromes. Basically, these two elements have to be same. These have to be same. So what we can do is, we can see if we can try to make sure that that the left and right characters are not same. Basically, for all index I, we need to make sure ai minus 1 is not equal to ai plus 1, or si plus 1 and si minus 1. So if these two are not equal, then we can say that there won't be any uh, for all index I. If the left and right indices are not equal, then we can say that all the indices I cannot be the middle indice of any odd length palindrome. So there cannot be any odd length palindrome since there are no valid middle indices. So now how can we make sure that no element has left and right equal? We can simply follow this trick. We can do A, B, C, D, E, and then A, B, C, D, E, and then again A, B, C, D, E, and again A, B, C, D, E. And we can just continue on printing this. What will happen is, basically, let's see for A, the left neighbor is E and the right neighbor is B. Again here for A is, it's the left neighbor is E and the right neighbor is B. Same E, B. Let's check for B. Again, the left neighbor is A and right neighbor is C. Left neighbor is A, right neighbor is C. Left neighbor is A, right neighbor is C. For C, left neighbor is B and D. For C, B and D. For C, B and D. Then for D, C and E, C and E, C and E. For E, D and A. For E, D and A, D and A, D and A. So basically, we made sure, if we print out a string like this, we are making sure two things, that no two consecutive elements are same, and the left and right neighbors are not same. So this makes sure that there are no even length palindromes, and this makes sure that there are no odd length palindromes. Basically, except palindromes with length 1, that would be 5, because we are only using 5 distinct characters. So since there are no even length and no odd length, so the total number of palindromes for a string like this would be 5, which uh, and since in the question we were asked to make a string which has less than equal to 5 palindromes, so this would be a good strategy to solve this question. So the time complexity needed to print this string is O of n. So this question will be solved in O of n. I'll show you guys the code. Basically, I had defined this string answer as A, B, C, D, E, and then for each I 0 to n, I just print answer of I modulo 5 and then enter. So this will, let me just show you a test case. This will print out A, B, C, D, E, A, B, C, D, E, and so on. So that was for problem B. Wait, is my screen not shared? It is shared, right? Okay, it's shared. So let's move on to problem C. So random name. There are n piles numbered 1, 2 till n. The ith pile initially has AI stones, and Alice and Bob are playing a name game on these piles, but there is a twist. As per the usual rules of NIM, Alice and Bob take turns alternately choosing a pile and removing some stones from the pile. With Alice going first, the player unable to make a move loses. However, the twist is that instead of choosing how many stones to remove from the pile, they have to use a random number generator. If there are x stones left in the pile, they will randomly generate an integer r between 1 and x and then remove exactly r stones from the pile. So in this game, find the probability that Alice wins modulo 9982. Okay, whatever. Then when both players play optimally, formally it can be shown that the answer can be represented as P by Q. So the test case time, the constraints are n is less than equal to 1000 and AI is less than equal to 1000 and sum of n does not exceed does not exceed 1000. So maximum time complexity that we can use is O of 1000n or O of n into AI, something like that, or maybe O of n square. So let's try to solve this. So problem C. Just a second. Not able, right? Hello, 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 hello. Okay, I think I'm audible. Hello, hello, hello. So, so problem C. We are given n piles of stones with AI stones in each pile. Alice and Bob are playing a game where Alice moves first and then Bob moves and then again Alice. So they take consecutive turns and in each turn, what they do is they can choose a pile and then remove a random number R from the pile. R stones from the pile. And whoever can't move loses. So basically, uh, and we need to find what? We need to find the probability that Alice wins. So probability that Alice wins. When will Alice win? Um, if the game ends with an odd number of moves. Basically, if the game ends with odd number of moves, then the last person to move would be Alice, and Alice will win. So basically, in simpler words, we need to find probability that game ends in odd moves, odd number of moves. So let's view some test case. Um, there aren't many test cases, so let's just take this test case 211. Now the Alice can either choose this pile or this pile, and since it's literally symmetrical, so there won't be any uh, there. First of all, there won't be any differences in choosing which pile, in choosing pile. So if Alice chooses this pile, then after Alice moves, the piles would look like this. And now Bob will have to choose this pile. So after Bob moves, the piles would look like this. And since Alice cannot move now, Bob wins. So the Bob wins with 100% probability. So the probability of Alice winning would be 0. Let's see this test case 1, 2, 1, 2. So Alice must choose this because there is only one pile. So there is half probability that the piles will look like this after Alice moves, or there is half probability that the piles would look like this. So in this case, Alice has won. But in this case, Bob will surely make this 0 and Alice would have lost. So 1/2 probability that Alice wins, that would be 1/2, and 1/2 modulo that mod would be this number. So that was for the test cases. Basically, one observation. It doesn't matter which pile is chosen in each move. Basically, in this particular rules of the name game, it does not matter which pile is chosen in each move, because since we need to find the probability that the game ends in odd number of moves. So basically, it does not matter that we need to find the probability that the game ends in odd number of moves, right? So the choosing which pile to remove elements from does not matter, because like all of the piles must go to 0 in the end. All of the piles have to go to 0 in the end, and since we are removing a random number of tiles, so somewhere in the during the moves, Alice or Bob, whoever, will have to choose that pile. Will have to choose the pile. So it does not matter if he chooses that pile at that time, or if he chooses it before that time, because the probability would be the same. So it does not really matter which pile is chosen in each move. We can choose any pile and still the probability will be the same. It doesn't affect the chances of winning of Alice or Bob. So this observation, I don't think I've made it clear. Uh, Let me try to explain it. Basically, let's say there are piles like this. So Alice basically, then if Bob chooses this pile, and then if Alice chooses this pile, then if Bob chooses this pile, then if Bob chooses this pile again, it doesn't matter. Bob could have chosen this pile at the second move, and still the chances of Bob winning would have been the same. So, like, he could have made this move earlier, but still the chances would have been the same, because someone else would then make this move, and someone else would have made this move, and someone else would have made this move. We just need to find the probability that the total number of moves needed to deplete all the piles to 0 is odd. So it doesn't really matter which pile I choose in each move. So let's just say that we would just start from the 0th pile and move till the nth pile after, and we would just start taking turns on this pile, and after this pile has fully emptied, we will do turns on this pile, and after this pile has fully emptied, we will do turns on this pile, and so on. So let's just fix this in the game. And now let's find the probability that it takes odd number of moves to deplete all the piles. So So let's try to find the subproblem in this question. We had piles like this, right? Let's take this and then this. So basically, let's say it took me odd number of moves to deplete this pile, right? I had moved and it took me odd number of moves to deplete this pile. So now to deplete all the piles in odd number of moves, I can take the sub problem of these piles in even number of moves. And let's say then this pile was depleted in even number of moves, let's say. So now I will have the sub problem of these piles depleting in again even number of moves, because since I had to deplete total in even and this pile took me even number of moves, so these two must take even number of moves. Now let's take that this pile then took odd number of moves. So then we will get the sub problem that this pile would need odd number of moves, because we need total even and this was odd, so this also has to be odd. So let's try to figure out the probability using these sub problems. Let's try to define a DP, which basically tells us the probability of the let me just write the state type. So what does this mean? The probability of depleting the piles I to n using basically type moves. If type is 1, then odd moves, and if type is 0, then even moves. So basically the probability of depleting the piles I to n using odd moves or even moves will be stored in this state. Right, and how can we transition? So basically, let's say I had to find the probability of depleting I till n in odd number of moves. So what I can do is I can multiply this. Let's just define this variable prob of I comma, let's say odd. So what this is? This is probability of depleting ith pile in odd moves. Basically, this contains for all I to n piles, and this is just for a single ith stone pile. We'll figure out how we are calculating this later. Let's just say that we have this for now. So dp of I comma odd will be probability that ith took odd number of moves, and then since ith took an odd number of moves, from I plus 1 we need an even number of moves. Also, the other case could be that the ith took an even number of moves. So we need to multiply I plus 1 till n took an odd number of moves. So this will give us the value of I comma odd. Basically, we need to add both these probabilities. This would be the value for this state. So this is our DP, and now we need to calculate the probability of depleting a stone pile in odd number of moves or in even number of moves. So depleting a stone pile in odd number or even number of moves. We need to find this. So how can we find this? Basically, let's say that probability of let's say that I need to deplete x stones, a pile which has x number of stones in odd number of moves. in odd. Let's just denote odd with 1 since we need states. So probability of depleting X number of stones in a pile using odd moves. What will be this probability? This probability will be summation 1 by X into probability of depleting X minus I, comma, this will be decided with parity. So basically I equal to 1 to X. So what is I? I is the random number that when I selected this pile, let's say that I got the random number I. So if I got the random number I, then X minus I would be basically a parity would be 0. Let me just 1 second. So parity would be 0. So I needed to deplete X stones in odd number of moves, right? So I make a move, I make one move, and in one move there are X different cases that could have happened. And each case is independent. So independent and equiprobable. We are given that here. They will randomly generate an integer R between 1 and X, inclusive and equiprobable. So basically getting I from 1 to X is equiprobable. So the probability of every event would be 1 by X, and then we can multiply this with the probability of depleting a stone pile with now X minus I stones and in even number of moves, because since we had to deplete X in odd number of moves and we made a move, so now there will be even number of moves left. Basically, if we have some odd number and we subtract minus from it, we get an even number. So if we had odd number of moves left and if we subtract minus 1 from it, we get even number of moves left. Or if we had to calculate probability of X comma 0, we could have again followed the same 1 by X probability X minus I comma 1. So this can be again calculated using DP. Let's analyze the time complexities for the DP that we are using. For probability DP, the number of states is equal to 1000 into 2, because the value of X is basically the number of stones in the pile. So the value of X can be till maximum 1000, and this can be 0 or 1. So 1000 into 2, and number of transitions, they can be again 1000. So the total probability, total time complexity would be 1000 into 1000 into 2, which is O of 10 to the power 6, which can pass easily. So also because since these values don't change for a test case, these values do not change. So we just need to do this O of 10 to the power 6 pre-computation. Since the value of probability of a stone pile of having X stones depleting in odd number of moves, this value is constant for all the test cases. So it does not change. So we don't need to calculate it over and over again. And we need to make a simple change in our DP transition. We just need to do probability A of I and probability A of I. So basically, now this will be the answer that when there are AI number of stones in a pile, what is the probability that it takes odd number of moves to deplete it? And since it is taking an odd number of moves to deplete the ith pile, from I plus 1th onward, we will need an even number of moves. So this will be the total probability that from I till n, the total number of moves taken would be odd. And similarly, if AI stones took even number of turns, then from I plus 1th onwards, we need to find the probability of odd number of turns, because even plus odd is odd and odd plus even is even. Even odd plus even is also odd. So similarly, I'll just write the transition once more here for a DPI odd and DPI even. So DPI comma odd This would be just probability of AI in even into dp I plus 1 odd, and plus probability AI odd into dp I plus 1 even. And similarly for dp I comma even, the transition would be probability AI even into dp I plus 1 even, and probability of AI odd into dp I plus 1 odd. And the base cases for this would be if I is equal to n, then if odd, return 0, and if even, return 1. Since if we reach till I equal to n, there aren't any more piles that we can deplete from, that we need to deplete. So we cannot take odd number of moves, since the minimum number of odd number of moves would be 1. So we cannot basically make any further moves. So odd number of moves cannot be made. So probability would be 0. And since we can do this in even number of moves, since 0 is an even number, so we will return 1. So this was for the DP, and let me write the for the probability again. So for prob AI, not AI here, basically x comma even would be summation 1 by x prob x minus I comma odd. And for prob x comma odd, it would be 1 by x prob x minus I comma even. And for base case for this DP would be prob of 0 comma even would be 1, and prob of 0 comma odd would be 0. This would be the base case. So time complexity of this is pre-computation. It happens outside the test cases since this is constant. So this is 10 to the power 6, and time complexity for this is O of n. Since the number of states is n into 2, and the transitions are 2 for each state, so O of n. So overall time complexity would be O of 10 to the power 6 plus O of Tn. Let me show you guys the code. um, this DP is this DP is basically prob this thing. We can see that this R is basically I in my formula. So prob is just mod inverse num, basically 1 by x. Since I'm calculating DP of num comma type, so 1 by num into DP of num minus R into this is basically inverting the types or 1. So num minus R, and this is inverted even odd even, and summation and return DP. So this and this line is for memorization. This was the transition. This was the state. Now this is the answer. This is this one basically. So for I comma type, we had DP, which is prob vi comma even into answer I plus 1. And since this is even, the type remains same. If this was odd, the type is odd 1. So that type is basically, if it was even, then it becomes odd. And if it was odd, then it becomes even. And this is memorization. So these are the two DPs. An answer of 0 comma 1 would be the answer, basically because we need to find the probability that it takes odd number of moves. So 0 comma 1. So that was for question C, the time complexity we have discussed. Let's move on to question D. Hello, hello. So minimum set, you are given an integer n. Let us call a set of pairs. Let us call a set of pairs of integer s equal to a1 b1, a2 b2, a3 b3, ak bk good if it satisfies the following conditions. So for every permutation p of the integers 1 comma n, it is possible to sort p with the usage of following operations as many times as you want. Choose x comma y belonging to s and then swap px and py. The cost of a set is defined as summation I equal to 1 to k and ai XOR bi, where XOR represents the bitwise XOR operator, and find the minimum cost of a good set. So the first line, so the constraints are t is still 10 to the power 3 and n is still 10 to the power 9. So expected complexity would be around log n or log square n something. So basically problem D. Uh, a set S equal to A1 B1, A2 B2, AK BK. This is if good if we can sort any permutation P using the operations swap AI BI any number of times. And we have also another definition, cost of a set. So cost of a set is AI XOR BI summation. So we need to minimize this cost for a good set S. So let's try to analyze when we will call a set good. So basically, a set is called good if we can use these swaps, actually swap P of AI and P of BI. So basically swapping these indexes, AI and BI are indexes. So if we use these swaps, we can sort any permutation P. We can swap any permutation P, sort. So to make sure that we can sort any permutation P, we must be able to place any element at any index. Basically, I'll try to explain my point. Let's say we have a permutation of size 4. So if we have a permutation of size 4, the one could have been here, or one could have been here, or one could have also been here in some permutation. Let me just take examples actually. So let's just take 2143 and let's take 2413 and let's take 2431. So there, in this permutation, after sorting, this one must go from this index to this index. In this one must go from here to here, and in this one must go from here to here. So basically, uh, one must be able to go from any index to the first index. And similarly, what I can do is for 2 again, I can write these test cases where the 2 are at different positions. And for from each of the positions, using the good set S, we need to be able to move 2 to the second index. So basically, from each we need to be able to place any element at any index. We need to somehow also need the ability to swap these two indices and these two indices and these two indices. We can use a series of swaps, but we must be able to always place any element from any index to any index. Only then we can say that we can sort any permutation. We must be able to place any element from some index I to an index j. We should be able to do swap between any, actually not swap, we should be able to place any element at any index. So to actually perform these swaps, there must be some kind of path. Basically, let's say that I need to put the element at ith index to the jth index. So there must be some path. Basically, I can first swap I and I1 so that now ith element is at the I1th index. Then I can swap I1th index to I2th index. And then I can maybe swap I2th to I3th. And then there is a swap possible from I3th to J. So there can be paths like this that I can use to put the ith element to the jth element at the jth index, ith index to the jth index. So basically, to ensure a path, we need to ensure a path exists between any two indices. We need to make sure that a path like this exists between any two indices. Only then the any permutation can be swapped, right? So uh, again, we can see it in this example. Basically, we had to have a path from 2 to 1. Here we had to have a path from 3 to 1. Here we need a path from 4 to 1. Similarly, here we need a path from 1 to 2, from 3 to 2, from 4 to 2. So basically, we need to be able to go from any index to any index. We need a path from all indexes to all other indexes. So uh, we can now visualize this as a kind of graph problem. How? What we can do is let me just show this for n equal to 4. N equal to 4. So what we have is 1, 2, 3, and 4. And there are edges from each vertex to each other vertex. Actually, these edges are not directed, so. And from 2 to 3, and from 3 to 4, from 1 to 4. Okay. 1, 4, 1, 2, 1, 3. Okay. So basically, we have this kind of situation where the weight of each edge is simply ones or two, twos or four, threes or four, ones or three, then threes or two, then ones or four. So we are given these weights, and then we need to select some edges out of these edges. We need to select some edges out of these so that they connect all the nodes and the sum of those edges are minimum. So this is actually a very famous problem, and this is known as the problem of minimum spanning tree. So minimum spanning tree. So actually, the algorithm to solve this problem of minimum spanning tree looks like this. Basically, we sort all the edges in ascending order of weights, of their weights. And then we try to add these edges in this order. And we only add an edge if it connects to unconnected nodes, previously unconnected nodes. So I'll show you guys an example, actually a dry run of this algorithm so that it is more clear. Let's just take any graph. Let's just take the graph that we had above and let's randomly put some weights. Let's say this is 3, 4, 5, 1, 7, and 2. Okay. So we need to process all the edges in ascending order. So first we will see the edge with weight 1. And since this edge is connecting, initially all the nodes are unconnected, right? Because we haven't chosen any edges in our for our answer. So let's check for the edge with weight 1. And since it is connecting to unconnected nodes, let's put this in our answer. And now let's check for edge with weight 2. And since these two are again unconnected, so we can connect them. And let's now check for edge of weight 3. Since again these two are unconnected, we can connect them. Now let's see for weight 4, this happens, and for weight 5, this happens. So you cannot get, oh, sorry, weight 5 we do not select because these two vertices have already been, actually weight 4 also we do not select. Okay, sorry. After 1, 2, 3, when we check for 4, we see that these two vertices are already connected by this path. So we do not take this edge, and then we check for weight 5 and we see that these two are already connected by this path. So we do not include this edge in our solution, and similarly for 7 also we do not include. So the minimum cost that required to connect all these edges would be 1 plus 2 plus 3. 5, 6. So let's try to implement this algorithm to find the solution for this case. So 1s or 2 is basically 3, 2s or 4 is 6, 1s or 4 is 5, 3s or 2 is 1, 3s or 4 is 7, 1s or 3 is 2. So we go in ascending order. First is 1. So we choose this edge. And then the next is this edge with weight 2. Again, these two are unconnected. So we choose this edge. Then this edge has weight 3. But since these were already connected, so we do not take this edge. Now, this edge has weight 5, and 1 and 4 are not connected, so we connect them. Now this edge has weight 6, but 2 and 4 are already connected, so we don't use this edge. And 3 and 4 are also connected, so we don't use this edge. So we'll require these 3 edges, and the sum of those would be 2 plus 1 plus 5, which is 8. Okay. So The time complexity that will require if we implement this algorithm on this question would be O of n square, because there will be n square different edges. Since there is an edge between each edge between every pair of two vertices, so there would be total of n square edges, and we need to iterate over all of them in ascending order. So the total time complexity would be O of n square. So we cannot use this algorithm directly. Let's try to exploit the properties of XOR, and let's see what we can do. So uh, obviously, XOR of two different numbers cannot be zero. Because since these two numbers are different, so at least one bit must be different for those two numbers. So at least one bit must be 0 1, which would be XORed to give 1, and so the XOR of two different numbers cannot be 0. So basically, minimum edge minimum cost of edge that we can get is 1. So basically, we'll have some edges that with cost of 1, which will be the like minimum cost edges. From there, we can start our algorithm. So let's try to solve this question for some graph. Let's say we can take from 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's try to solve for this. Okay. So first we look for all the edges with cost 1, right? So and if the edges with cost 1 are between two unconnected nodes, then we can connect those nodes, right? So what nodes will have a cost of 1? So basically it will be like this. 2 and 3 will have a cost of 1 because 2 or 3 is 1. And then 4 and 5 will have a cost of 1, 6 and 7 will have a cost of 1, 8 and 9 will have a cost of 1, 10, 11 will have a cost of 1, 12, 13, 14, 15. So basically, because 2 is 1, 0 and 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 1, 1, 0, 1, 6 is 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 2, 4, 8, and 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, and 14 is 1, 1, 1, 0, and 1, 1, 1, 1. So we can see that even numbers have this last bit 0 and odd numbers have this last bit 1, and rest would remain same between two consecutive even and odd numbers. So basically these two we can connect all these pairs, right? Now there aren't any more costs with any more edges with cost 1. So now let's look for cost 2. Cost 1 is done, which is basically even odd pair. Now let's look for cost 2. So for cost 2, the first number must have the second bit 1 and the second number must have the second bit 0, and rest all should be same, right? So the difference between these two would be -2. So if this number is x, this number must be x minus 2, and this number, since it has a second bit set, then x by 2 must be an odd number. Floor of x by 2. So since x by 2 is an odd number, then second bit would be 1. So let's see which numbers what numbers x by 2 what numbers when divided by 2 are odd. So these two are odd and these two are odd. These are not odd because 4 by 2 is 2 and 5 by 2 is also 2. So these two are even, these two are odd. Similarly, these two are even, these two are odd, these two are odd. So what we can do is connect x to x minus 2, because since x has this bit set, then x minus 2 must have this bit unset and rest must remain same. So what we can do is connect 3 to 1, we can connect 5 to 7, we can connect 9 to 11, then we can connect 13 to 15, and similarly this. Oh, right. So now there aren't any more cost of edges of cost 1, but we have gotten now several different connected components. Now this has formed a connected component. This is another connected component. This is another connected component. And this is another connected component. First one has a size of 3 and rest of them has a size of 4. Also in the last step, the first one had a size of 2. First one had a size of 1 and rest of them had sizes of 2. So basically size has doubled for most of them. So now let's try to find for cost of edge 3. Wait just a second. Cost equal to 3, let's try to find. So what pairs of number can give cost equal to 3? They must be like this. First number must have these two bits set, and the next number must have these two bits unset, and rest must be same, right? So the difference would be -3. And what numbers will have these two bits set? They would be of the form 4k plus 3, because k can be any number, and then if we multiply by 4, we are basically shifting it by 2 bits. If k was 11001, and if we multiply it by 4, it becomes 11001 and then 2 zeros extra. And then if we add 3, this becomes 11. So basically numbers of the form 4k plus 3 have these two bits set, and so 4k plus 3 can be paired with 4k to get cost of edges 3, uh, edges of cost 3. But we see a problem. Basically the candidates for 4k plus 3 would be 3, 7, 11, 15. But we see that 3 has no prior 3 minus 3 is 0. We do not have a 0 as node. And 7 minus 3 is 4. And we don't want to make this connection because 7 and 4 are already connected. Basically in the algorithm, we had a condition, we only add an edge if it connects to previously unconnected nodes. So 7 and 4 we won't connect. And again, the next number, basically 11 and 8 we won't connect, and then 15 and 12 we won't connect. So for 4 we are not connecting. Let's try to see for 3 we are not connecting. Let's try to see for cost equal to 4. So for cost equal to 4, again similarly we'll have this, sorry, we'll have the third bit in one number, and it would be unset in the other number, and rest of it must remain same. So the difference would be -4, and for a number to have the third bit set, x by 4 floor must be an odd number. So let's look what numbers are odd when divided by 4. So these 4 numbers would give 1 when divided by 4, so these can be used. And similarly, these 4 numbers would give 3 when divided by 4, so these can be used. And we can make edges from x to x minus 4, right? So what we can do is we can make an edge from 7 to 3, or we can make an edge from 6 to 4, or we can also make an edge from 5 to 1. We cannot make an edge from 4 because that would be 0. 0 we don't have. So we can just take 5 to 1. And now these two are also connected. And similarly here we can choose any. So let's just choose 15 to 1. Again 12. So we can choose 15 minus 4, 11 to form this edge, and now these two will be connected. And since there aren't any more numbers, there aren't any more connections that we can make from this cost equal to 4 edge. Let's move on to cost equal to 5 edge. Basically, we could have used these 4 elements or these 4 elements to form cost equal to 4 edges. But we can only use any one of them, because if we connect 15 to 11, all these elements are now in the same connected component. So connecting 14 to 10 or 13 to 9 or 12 to 8 would just be a waste. And also in our algorithm, we are not allowed to do that. So we'll connect any one and then we'll move on. So let's move on to, let me just redraw this actually. So now we have two connected components, 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10, 11, 12, 13, 14, 15. We'll have these two connected components. And now let's move on to check for cost equal to 6. So for cost equal to 6, again, these two second and third bit must be 1, and rest of them can be anything. They must be same, and these two must be unset in the another number. So the difference would be of 6. And for a number to have these two bits set, it must be of the form where basically 8 8 into k plus 6. Yep. Okay. This is second and third bit. So yeah, 8 into k plus 6. Basically what this will do, k can be any number. Let's take this. And if we multiply this by 8, it will have now 3 more zeros in the end. And if we add 6, these two bits become 1. So any number of this form will always have these two bits as 1. So let's see what numbers are of the form 8k plus 6. It is 1 plus 14, right? And since the difference is 6, we can make the edge from 14 to 8. But we are not doing this because 14 and 8 are already in the same connected component. So this adding this edge would be useless. Or another number is for k equal to 0, we get this 6. And again, 6 minus 6 is 0, and 0 is not a node. So we will not connect that edge. So let's now see for cost equal to 7. Similarly, 8k plus 7 we'll get, and 8k plus 7 is 15. And 15 we can connect to 8, but we will not perform this connection since it is again of the cost, since both of them are already connected. So let's look at cost equal to 8. So for cost equal to 8, x upon 8 must be an odd number, and x can be connected to x minus 8. So x upon 8 must be an odd number. So all of these are valid candidates. And so if we can make x edge from x to x minus 8, we can use any of these number to connect to any of these numbers. So basically, let's just connect 11 to 3. That would give us the answer. So this was the basically dry running the algorithm on this array. Let's just recap on what we actually did. So first we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we made some connected components. We did this, we did these connections. And then basically what we did was connect this to this, connect this to this, connect this to this. connect this to this, connect this to this. And then we got this connection 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now what happened? This was for cost edge equal to 1, cost 2. Now we try to look for cost equal to 3, but cost equal to 3 was not like a good choice because 40 plus because we could have only made edge from 7 to 4 or from 11 to 8 or from 15 to 12. Basically, cost edges of cost 3 were not valid to perform, not useful to perform. So we then moved on to cost 4, and then we connected these components, this component, sorry, these. Okay, I think sorry, we did not connect. We connected these. We did not connect this. I made the connections a little wrong. Actually, we connected this. We connected these. We connected we connected these, and we connected these. So what we got was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15. And then we connected this and this. So then we got 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10, 11, 12, 13, 14, 15. So this. And then again, similarly, we connected these two. And also, we were not able to perform for cost equal to 4, cost equal to 5, 6, and 7. Right. Yep. Yep. So for cost equal to 5, 6, 7, we were not able to perform because for cost equal to 5, it will be 8K plus 5. And 8K plus 5 is basically 13 to 8, which is not a good connection. And here 8K plus 5 would be 5 to 0, which is another not good connection. So similarly for 6, it would be from 14 to 8. For 7, it would be from 15 to 8, which are not useful connections. So we moved on to cost equal to 8. And for cost equal to 8, we can connect any of these from to these. This node cannot be connected, right? So this is our algorithm. We are seeing that we only make connections of cost in powers of 2. This is our first observation. And there is one exception to this case. Let's try to see what would have happened if we had a 16 here. So first of all, 16 does not have any edges of cost 1, 2, 3, 4, 5, 6, 7, 8. So it would have been unconnected till this point because 16 looks like this. 1, 2, 4, 8, 16. 1, 2, 4, 8, 16. Yeah, 16 looks like this. So it has only one edge, which is of the basically it all the edges that it can make to its previous ancestors would be having cost greater than 16 because all these bits are 0 and all these numbers would have some ones in these bits and they all have this bit as 0, so this will always remain 1 in the XOR. So 16 would have not made any connection till now. So let's look at this case where 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 are in one group, and then we have 16 in another. So basically, according to our algorithm, the next edge would have been formed at cost equal to 16, right? Because 7, 8, 9, 10, we saw that we are not able to perform those edges. So the next edge would have been possible for cost equal to 16. But what happens is basically I showed you that this node is not able to perform the connection because the connection is from x to x minus 8, right? So 8 to 0 is not able, we are not able to perform that connection. Similarly, from 4 to 0, we were not able to perform. Similarly, from 2 to 0, we were not able to perform. So, from again from 16, we are not able to make that connection. If we had 17 here, we could have performed this connection, 17 to 1, and then the answer would have been the same. We could have followed our algorithm and we would have gotten the same answer. But since we had the last but since we have the last element as 16, we cannot perform the 16 cost. So we will have to go with this 16 plus 1, 17. This is a cost of 17. This is the special case where n is a power of 2. And in this case, whatever the cost we get from our previous algorithm, we will just plus 1. And now let's try to generalize our previous algorithm. Let me again make the connections actually, and let me do it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So initially, what in the first step, these, 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 these make a connection. And then what happens in every subsequent step is that uh, every pair gets connected. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15. So these gets connected. And then again, similarly, these two and these two gets connected. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now again, these two get connected. So we get 1, 2, 3 till 15. This was cost equal to 1. This was cost equal to 2. This was cost equal to 4. And this was cost equal to 8. So basically, if we have X number of groups at any stage, uh, we make X by 2 new connections to go from this state to this state. Since we had 4 here, we performed 2 connections to get 2. And since we had 1, 2, 3, 4, 5, 6, 7, 8 here, we performed 1, 2, 3, 4 connections. Also, if we had, let's say, till 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in the first step, this, and this will be connected. And then again, similarly, these, this, and now this cannot be connected to anyone. So basically, we will get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, this. So basically, since we in the first step, we had 1, 2, 3, 4, 5, 6, 7 groups. So 7 by 2 floor, 3 new connections were made. And then we will get 4 new groups, so forth. And cost of each subsequent transition would be doubled. So 1, 2, then we will get 4, 8, and so on. So let's dry run this on 100. So initially 1, 2, 3, 4 till 100 we will have like this. And in the first step, 2, 3, 4, 6 and 98, 99 will make a group. And 100 would be left without a group. So how many groups are in the first step? These are from 2 to 4, 98. This is 49. This is 1 and this is another one. So 51 groups after the first step. So basically, actually the first step is an exception because it depends on whether we had even number of or odd number of groups. So basically, in this case, we always we are making a number of connections basically equal to number of total number of even integers minus one. Basically, last even integer we will not take, and if it ended with an odd number, then it's fine. Total number of even integers would be the answer. So for even, it would be 100 by 2 minus 1 number of connections, and for odd, it would have been 99 by 2 number of connections. 52 and 44.5. So, yeah, 40, what? 49, right? 48 point. Actually, let me do this. So, see, what is 49.5? Yep, 49 and 49. So this is just the starting point, because in starting we can only make connections from even number to odd number. So we had 51 connections, and now this will happen. So we will get 51 minus 51 by 2, which is 51 minus 25, which is 26 new groups. So 25 connections were made. So 25 into 2, here 51 into 1, actually 49 into 1. And now from 26, we will get 13 new groups, 13 into 4. And from 13, 13 by 2 is 6. So 6 into 8, we will get 7. From 7, 7 by 2 is 3. So 3 into 16, we will get 4. From 4, we will get 4 by 2, 2 into 32. So 2. And from 2, we will get 1 and 1 into 64. So the total cost is 64 plus 64 plus 48 plus 48 plus 52 plus 50 plus 49. So this comes out to be 128 plus 96 plus 102 plus 49. This is 4, 1 carry, 11, 12. 224 plus 151, which is 375, which is the answer. So that was for the question. I'll show you guys the code. Time complexity is over log n, because we are reducing the number of groups by floor. So basically, initially answer is 0, and the number of groups is n by 2 plus 1, which would be 100 by 2 plus 151, or 99 by 2, which is 49 plus 99 by 2, which is 49 plus 150. So in the case of 99, this won't be a group, and in the case of 100, this will be a group. So 49 and 50. And answer would be n minus groups, because that is the number of edges made in the first step. Then we do a while loop, and in the while loop, we make groups by 2 new connections and reduce the groups by 2, and increase the multiplying factor by 2, because the cost is increasing by 2. And this is for the special case where n is the power of 2, because we cannot make that last connection in the proper cost. So we'll need one extra cost for that, because we XOR it with 1. And that is, then I see out the answer. So that was for problem D. Let's move on to problem E. So permutation counting, this is the easy version of the problem. Here k is fixed to be 3. You are given two integers n and k. Count the number of permutations p of the integers 1, n, satisfying the following conditions: pi plus 1 mod k not equal to 0. Since the answer may be large, output it modulo this. The first line of input will contain a single integer t. Denote the number of test cases. First and only line of each test case. So n is given as 2 into 10 to the power 5. So expected time complexity would be, and sum of n does not exceed 2e5. So expected time complexity would be 2e5. So basically, problem E, we need to count number of permutations such that pi plus 1 mod k is mod 3 actually for this question is not equal to 0, right? So let's just first use the property of modular arithmetic to write this as pi modulo 3 plus pi plus 1 modulo 3 whole modulo 3 is not equal to 0. Basically, a plus b mod 3 mod m is equal to a mod m plus b mod m whole mod m. So using this property, I could write this. And now I can see that for an integer pi, only its value modulo 3 is actually valuable for us. Basically, two integers 1 and 4 would be the same in this equation, since 1 modulo 3 is 1 and 4 modulo 3 is also 1. So we can see that both of them hold the same value in this equation. So let's just the first step for this problem would be uh, since it is modulo 3, the modulo 3 could only be 0, 1 and 2. So let's just count number of numbers from 1 to n with mod 3 equal to let's say for 0 the count of number is x, and for 1 the count of number is y, and from for 2 the count of number is z. So we only need these counts because using this count we can solve the question, because only the modulo 3 value actually holds importance. So let's try to see, let's try to denote this number as a, denote this number as b, denote this number as c. So let's just imagine that the permutation has somewhere the number a. So what can be the next number after a? We can have b. After a, we can have c as well. But after a, we cannot have another a, because if we have this as a and this as a, then 0 plus 0 mod 3 would be equal to 0, and that would, we don't need that. We don't want to count that. So after a, we can have b. After a, we can have c. After a, we cannot have a again. So this is valid and this is valid. Let's see for b. After b, we can have a, and after b, we can have b. But after b, we cannot have c. For c, after C, we can have A. After C, we can have another C. But for C, we cannot have B, because 2 plus 1 would be 3. And 3 mod 3 would give us 0. So only these mutations where all the consecutive elements are from this set. So let's try to analyze this a bit. Let's look at this. So this means that no 2A can be consecutive in the permutation. From this, we observe that no 2A can be consecutive, since that would be an invalid edge. So no 2A can be consecutive. So our question, basically in our question, we can like separate all the A's from each other. And now we need to fill these gaps with at least one B or one C. We need to fill this gap with some element other than A, so that all A's are separated. So what we can do? Basically, A can make now connection with B or C both. So A doesn't have a problem with whatever numbers we fill here, unless and until they are not, they should not be A. Okay. So now let's see for B. Now if I place a B here somewhere, what will happen? B can only make an edge with B and B can make an edge with A. So basically, I can have this kind of thing, and I can maybe have some B here as well. So I can only have this kind of thing. I cannot have a C in between here. And similarly for C also, I cannot have a B. I cannot have any B's connected with C's. So basically, B must start after an A and B must end at an A. C cannot come in between two A's where B are also present. So basically, we need to make groups of B and C and place those groups between A's. Basically, let's just say I have 5A and 3B and 7C. So what I can do, I'll just show a valid configuration. I can like place 2C here, 2C here, 1B here, 2B here, and then maybe for 3C here. So this is a valid configuration. Since all the groups only contain with the same element, it's either C's or it's either B's, and all A's are separated from each other. So this is a valid configuration and we need to count these configurations, right? So let's try to further analyze the question. So I have separated all the A's, and since the number of A's are X, so what I can do is I can either fill these gaps. Let's take 5A. So I can either fill 1, 2, 3, 4 gaps, or I can actually create a gap here and I can fill 5 gaps. Similarly, I can remove this. I can remove this and add a gap here. So again 5. And I can take both of them. So 6. So basically for X number of A's, I need to solve for X minus 1 gaps, X gaps 2 times, and X plus 1 gaps. Basically, since here A was 5, so 4, which is X minus 1, X and X plus 1. So X minus 1 gap, or 2 into 2 times X gaps and X plus 1 gaps. So let's try to solve this question for, let's okay, so let's try to find number of ways to fill X gaps. So basically to fill X gaps, actually X was the number of A. Okay, fine. So basically to fill X gaps, what I can do is I have B and C, right? So maybe what I can do is I can make one group of B and X minus 1 groups of C, or actually 0 groups of B and X groups of C, or 1 group of B and X minus 1 group of C, or 2 group of B and X minus 2 groups of C, and so on till X groups of B and 0 groups of C. Also note that it's not really important current right now, but 0 groups can only be possible when Y is equal to 0. Okay. Y was the number of elements of type B. So if basically, yep. So X is type A, Y is type B, and Z is type C. So only if Y is equal to 0, only then we can form 0 groups of B. Because if Y is some positive number, then how can we make 0 groups of some X numbers, some X quantity? We at least need to make one group. So now Let's try to individually calculate for each pair. So let's say that for B, I need some G1 groups, and for C, I need some G2 groups, right? So let's count the number of ways I can get G1 groups, and let's count the number of ways I can make G2 groups, and let's count how can we arrange them in the gaps, G1 plus G2 gaps, right? So how? Let's just first solve the problem of distributing X items in G groups. If we solve this problem, then we'll know how many ways we can distribute B in G1 groups and how many ways we can distribute C in G1 groups. So what we can do is basically place all the X items like this, right? And then we can place some bars in between, or more specifically G minus 1 bars. What will happen if we place G minus 1 bars in between? This will create G different groups. So the number of ways to place G minus 1 bars in between X items would be the number of ways to distribute X items in G groups. Also, the bars must be between two elements. So there are only X minus 1 possible places to place the bar. Basically for 1, 2, 3, 4, 5, we can either place the bar here, 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 or here. We cannot place some bar here or here, because that does not distribute the items in groups. So we only have X minus 1 positions, and we need to select G minus 1 positions out of those. So to distribute X minus 1 in X items in G groups, the number of ways would be X minus 1 C G minus 1. So this is the number of ways to distribute X items in G groups. So what we notice is number of ways to distribute B items in G group would be B minus 1 C G minus 1, and number of ways to distribute C items in G minus 1 groups would be C minus 1 G minus 1, right? Or actually B was the not B, Y and Z. So Y and Z. So this is the number of ways to distribute both of them. And since these two are independent from each other, total number of ways would be multiplication of these two, because each configuration of this can be matched with each configuration of this. So this is multiplication. Also, another G1 plus G2 into a C G1. This is basically selecting, since we need to fill G1 plus G2 gaps, right? So we need to first select G1 gaps out of those which will be filled by B. So first we select the G1 gaps, then we fill it with B, and then for the rest of the gaps, we fill them with C. So this is the number of ways to fill G1 plus G2 gaps with G1 groups of B and G2 groups of C. So using this formula, we can now calculate for each of these, and total sum of each of these would be the number of ways to fill X gaps, and we can similarly repeat the process for X minus 1, X and X plus 1 to get the answer. So this can be calculated in O of log n with a little pre-calculation. And since X can be a maximum of n, so this will be total n different things that we need to calculate. So this would be done in O of n log n. And since we need to calculate it for X minus 1 and 2 times X and 1 time X plus 1, so O of 4 n log n. So this will be the final time complexity. I'll show you guys the code. So basically, I'll first mod inverse and binary exponentiation. This is NCR. I have some conditions. Basically, if R is negative, then I return 0. And if N is less than R, then also I return 0 because we cannot select R items from N if N is less than R. And if N equal to R, then I simply return 1. And this is simply NCR, N factorial upon R factorial into N minus R factorial. This is pre-calculation of factorials. So I take the input N and K and I calculate X, Y, and Z. Then for X minus 1 number of groups, basically P is I am iterating over these values. Iterating over these values. So this is NCR X minus 1 CP, basically G1 plus G2 CG1. Since we had X minus 1 gaps and we need to select P, so X minus 1 CP and X minus 1 CP. And then I'm distributing Y in P groups. And then I'm distributing Z in X minus 1 minus P groups. Because since Y was distributed in P groups, Z will now be distributed in minus 1 minus P group. So X minus 1 we have solved. Similarly, for formula we had basically X, X to X plus 1. And similarly, since we are choosing P from Y, so from Z we will choose X minus P, and here we will choose X plus 1 minus P. And also in the end, we need to multiply with factorial of X, Y, Z because this will basically count the permutations of individual numbers. Basically, we were treating all numbers as identical up till this point and calculating the answer. And now since they can be permutated with each other and still the permutation would be a good permutation, so we can just multiply with factorials of X, Y, Z and that would give us the answer. So this was for question E, and the time complexity would be these operations are log n and this is O of n, so O of n log n. That's it. So this was the discussion for CodeChef Starters 200. Thank you.